Hi there, Mr. Sutton here with the BC Calculus 7-4 Part 2 homework solution on Taylor series. On this problem, they want the third order Taylor polynomial for this f of x function at x equals 1. Since I'm not centered at 0, I'm going to use my general Taylor formula with x minus 1s and with the derivative at 1. So let's start by finding the function value at 1, f of 1. That's going to be, let's see here, since I'm just plugging in 1 for all these x's, I've essentially got 2 plus 1 plus 3, which is a total of 6 so far, minus 8 gives us negative 2. Next, let me find f prime of 1. So that's going to be 6x squared plus 2x plus 3, evaluated at 1. So that's going to be 6 plus 2 plus 3. That's a grand total of 11. Let me do the second derivative at 1 now. That's going to be 12x plus 2 evaluated at 1. So that's going to be 12 plus 2, or 14. And then finally, since I want third order, that means I need third derivative. So that's going to be just 12. And if you plug in 1 to 12, you still get 12. So let's build our series now. We have f of 1, which was negative 2, plus f prime of 1 times x minus 1. So 11 times x minus 1. Next, we're going to have 14 x minus 1 to the second power over 2 factorial. And finally, we'll have plus 12 times x minus 1 cubed over 3 factorial. And I could simplify this, but I'm just going to leave it the way it is. On this problem, I want the first 4 non-zero terms in general term of a series for ln of x about x equals 1. So I'm going to have to find function values and derivatives of ln of x at x equals 1. Let me start with just plain old f of 1, the ln of 1, which is 0. Unfortunately, that's not going to count towards our first 4 non-zero terms, so let's keep going. F prime of 1, that's going to be x to the negative 1, or 1 over x evaluated at 1, and that's just going to be, well, 1. Next, f double prime of 1, now I've got negative x to the negative 2 evaluated at 1, so that's just going to be negative 1. X to the, or 1 to the whatever power is just going to be 1. So it's really just the coefficient that's going to make the difference on all of these. So we've got negative 1. F triple prime of 1, now we've got 2x to the negative third. Plugging in 1 to that, we've just got 2. And we need fourth derivative because we only have 3 non-zero terms so far. So fourth derivative, that's going to be negative 6x to the negative 4. Plugging 1 into that, we end up with negative 6. All right, building our series now. F of 1 was just 0, so we're not going to bother writing that. Now we've got 1 times x minus 1, minus 1 times x minus 1 squared over 2 factorial, plus 2 x minus 1 cubed over 3 factorial, minus 6 x minus 1 to the fourth over 4 factorial. And we could keep going. We're going to have to write the general term at some point. Before I do that, though, I'm going to retrace my steps and simplify all these a little bit, because right now I'm not really seeing a clear pattern. There is one, I just don't see it very well. I think if I simplify this, it'll become more apparent what's going on so that I can get my nth term. So I've still got x minus 1. I can just rewrite this without the factorial downstairs. This next one, though, I've got 2 over 6, which means I've really just got 1 over 3 for that coefficient. And for this next one, I have negative 6 over 24, which is negative 1/4. I think I can get a general term out of this now. So in general, I've got x minus 1 to the nth power over n, no factorial anymore, because those factorials keep canceling out with the derivative upstairs. But now how about that first term, or the first piece of this term? Since I'm alternating, I'm going to need negative 1 to some power. Now normally I do negative 1 to the nth power, but if I want my first term, which must have an n value of 1 for me to get x minus 1 to the 1 over 1 here, if I want this first thing to come out positive, I need to be doing negative 1 to an even power. So I need to do negative 1 to the n minus 1 or n plus 1. I'm just going to do n plus 1. Doesn't really matter either way. So there we go. On this problem, they're giving us that p is the second degree Taylor polynomial for e to the negative 2x about x equals 3. Based off of this, they want the slope of the line tangent to the graph of p at x equals 3. Well, the second degree Taylor polynomial is accurate up to 2 derivatives in terms of information it shares with the original function. It has the original function value at x equals 3. The first derivative and the second derivative are all the same as the function e to the negative 2x. So if I want the slope of the line tangent to the graph of p, I'm basically asking for the first derivative of p, which is going to be the same as the first derivative of e to the negative 2x evaluated at 3. So the first derivative of e to the negative 2x is just negative 2 e to the negative 2x. If I just plug 3 into that to get that first derivative, I just end up with negative 2 e to the negative 6. And that is one of the answer choices, choice A. For this problem, they're saying the Taylor polynomial of degree 100 for some function about 3 is given by this series here. We want the value of the 30th derivative of 3. Well, the 30th derivative of 3 is going to be tied into the coefficient for x minus 3 to the 30th power. So what we're going to do is we're going to figure out what that coefficient ought to look like just based on our general Taylor formula, and then we're going to compare it to what the coefficient actually is in this series. So from our Taylor formula, we should just have a coefficient for x minus 3 to the 30th of derivative of 30th derivative of 3 over 30 factorial. So this is what the coefficient ought to look like. Now let's see what the coefficient actually does look like. So we want to find x minus 3 to the 30th. Looking up here, we have x minus 3 to the 6th, and then a whole bunch of dots, some general term, and we go all the way to x minus 3 to the 100th power. So this is not really satisfactory. We need the x minus 3 to the 30th. So to get that, we have to figure out what value of n we need to plug into this general formula, and then if we plug in that n value, we can figure out the 30th degree term. So looking at the pattern here, it looks like that for every n on our factorial end, we actually have an exponent that's twice that. So at n equals 1, the exponent is 2. At n equals 2, the exponent is 4. At n equals 3, the exponent is 6. So we're always doubling the exponent, which means if you want the 30th power, you need to take half of that to get the actual n value that you plugged in here. So that means that 30th power, we should have an n value, and this is from the series now, we should have an n value of 15 for degree 30. Plugging that into our general formula, that means our coefficient for the 30th degree term is going to be negative 1 to the 15 plus 1, and then we'll have 15 factorial downstairs. So this just becomes 1 over 15 factorial. All right, so here's what the coefficient ought to look like. Here's what it actually does look like. We're just going to compare these two things now, set them equal, and at this point I can just go ahead and solve for my 30th derivative. To do that, I'll just multiply both sides by 30 factorial. So that's 30 factorial over 15 factorial. Careful, the factorials do not just cancel out. This is actually one of the answer choices, thankfully, choice E. So we're going to pick that and call it a day. For this problem, I have an f function with the following information about f and its derivatives at x equals 3. We want the third degree Taylor polynomial for f at x equals 3. So my general setup on this one, I'm going to have f of 3 plus f prime of 3 times x minus 3 plus f double prime of 3 times x minus 3 squared over 2 factorial. And then I'll have triple prime of 3, x minus 3 cubed over 3 factorial. Whole lot of 3's in that last one. So plugging specific things in, that means we've now got 2 minus just 1 times x minus 3, so minus x minus 3. Now we've got 6x minus 3 squared over 2 factorial, and 12x minus 3 cubed over 3 factorial. But that's none of the answer choices. It looks like they simplified a little bit. So we've got 2 minus x minus 3, and then 6 over 2 is just 3 times x minus 3 squared. 12 over 6 is going to be 2x minus 3 cubed. Looking at my answer choices now, we need a 2 minus x minus 3, so that narrows it down to choices A through C. The next term needs to be 3x minus 3 squared, so now it's down to A and B. And this last term decides it, 2x minus 3 cubed, that gives us choice A. For this no calculator free response problem, we've got the differential equation dy over dx equals 6x squared minus x squared y. That's going to be a fun one. And f of x is some particular solution with an initial condition of -1, 2. First task, using Euler's method, two steps of equal size, starting at x equals -1, which is fortunate because they gave us the y value there. We want to approximate f of 0. So just our strategy here, to do this in two steps, we're going to have to go with step sizes of 1/2. So we're going to start by figuring out approximately f of -1/2. And then once we've got that approximation, we'll use that to figure out f of 0. So f of -1/2 then, that's going to be f of -1, that's our starting point, plus the derivative at -1, so f prime of -1, times our step size of +1/2. So f of -1, we actually already got that. That was 2. Now f prime of -1, to figure that out, we're going to have to plug in the point -1, -2 to our differential equation up here. So I'm going to have 6 times -1 quantity squared minus, this is going to be -1 squared times 2, the y value 2. So this is going to be 6 minus 2. This -1 squared just becomes a 1. 6 minus 2 is 4. So this is now 4 times our step size of 1/2. So this is really just 2 plus 2, which comes out to 4. So f of -1/2 then is approximately 4. Okay? Now that we've got that, we're going to figure out f of 0. I was about to say positive 0, but that would be silly. So f of 0. This is going to be approximately equal to this f of -1/2 that we just found, plus f prime of -1/2, times our step size of 1/2. f of -1/2 we said was approximately 4, so we're going to use that value there. For f prime of -1/2 now, we're going to have 6 times the x value, -1/2. Then we're going to have minus -1/2 squared times the y value, 4. We're going to use the approximated y value at -1/2. So this is going to be, let's see here, 6 times 1/4, so 6 over 4. And then over here, this is 1/4 times 4, so 1. So 6/4 minus 4/4 is going to be 2/4, or just simply 1/2. So now we've got our derivatives is really just 1/2 times that step size of 1/2. And you could leave it like this because it's all constants, or you can say 4 plus 1/4 is really 16/4 plus 1/4, which is 17/4. For this part of the problem, at the point -1, 2, the second derivative is -12, they're telling us. We want to find the second degree Taylor polynomial for f about x equals -1. Okay, so let's go ahead and use our Taylor setup here. So in general, if we're centering about -1, we should have f of -1 plus f prime of -1 times x plus 1, that's x minus -1, plus f double prime of -1 over 2 factorial times x plus 1 squared. So this is our general setup, and we've got just -1 for the a value in our Taylor formula. Now let's plug in some actual values. So f of -1, we already know that that's 2. F prime of -1, we found in the last problem part, that came out to a value of, I believe it was 4. So we have 4 times x plus 1. And then f double prime of -1, well, they essentially told us that right up here. It's -12. So we have -12 x plus 1 quantity squared over 2 factorial. And if you wanted to simplify this, you could make this last piece just minus 6 x plus 1 squared. There was no need to simplify it, but you could have. Either way, there's our polynomial. For this last problem part, they want the particular solution to this differential equation with the initial condition that they already gave us up here. I'm not sure why they specified it again, but there we are. So on this one, we notice that we have a y, an output variable, in the differential equation. That means we're going to have to separate our variables and get y with dy and dx on the other side. Before I can do that, though, I need to factor so that I can turn y into a multiplier to get it over here. So I can actually factor out and x squared. That leaves me with 6 minus y inside. And now I can divide both sides by 6 minus y. That gives me dy over 6 minus y, or 1 over 6 minus y dy. And then let me just multiply by dx to get it over with the x squared. Antiderivatives on both sides. On the left side, I've got ln absolute value 6 minus y divided by the tail of negative 1, so negative ln absolute value 6 minus y. And we'll have to resolve that absolute value a little bit later, but we'll hang on to it for now. Next, on the right side, this is going to be 1 over 3 x to the third plus c. And now to figure out my c value, I have to plug in my initial condition of negative 1 comma 2. So on the left side, I've got negative ln of 6 minus 2 in absolute value, although we don't really need it at this point. Over on the right side, this is 1/3 negative 1 to the third power plus c. So on the left side, this is negative ln of 4. On the right side, this is negative 1/3. Let me just add 1/3 over to the left side to get c alone. So that's going to be 1/3 minus ln of 4. Okay, now before we plug in our c value, we need to take care of this absolute value. Looking at my initial condition, my initial y value is 2. So if y is 2, that means that this 6 minus y stuff is going to be positive, which means that I can just replace the absolute value with a regular parentheses. I don't have to negate anything inside. So I'm going to rewrite this now as negative ln of parentheses 6 minus y equals 1/3 x cubed. And now we have the c value that we're adding in there, so plus 1/3 minus ln of 4. Now I have to isolate y. So to do that, my first step, I'm going to negate everything. So I've got ln of 6 minus y equals negative 1/3 x cubed minus 1/3 plus ln of 4. Next, to get rid of ln, I have to raise e to both sides. So I can write on the left side 6 minus y, because e and ln just cancel out. On the right side over here, I'm going to do e to all of this stuff. But I know that I can separate off this. I can separate out, if I have a plus ln of 4 in my exponent, then I can make this times e to the ln of 4, which I know is just 4. So I'm going to end up with 4 really as a coefficient out in front because of this ln of 4. And then for the rest of it, I've just got e to whatever else was left in my exponent. And a couple more steps here. I need to subtract 6 from both sides to get negative y by itself. But then I have to negate everything. So when the dust settles, I guess you could actually just add y over here and subtract 4 times e to all of this stuff over here. So you just end up with 6 minus 4e to the all of that stuff in your final answer.